So I have 1 hour today to talk to you guys. This is a very small room. It's even smaller than yesterday, but good morning. I had a very interesting night with my wife last night, who's in the crowd watching. So today we're going to talk about a bunch of old smart cards. These aren't new, but you guys got to crawl before you walk. You know, so if you're trying to get into reverse engineering ICs and stuff, this old stuff is the best stuff to get into because it's large. And everything you're going to see today was optically imaged versus yesterday you saw SEM-based images, scanning electron microscope. So these smart cards secured millions of dollars in revenue for companies, and they were considered secure. And even today, I talked to a gentleman yesterday talking about the SLE78 from Infineon, and I've looked at it, and I can tell you that the engineers that designed the SLE78 from Infineon are not the same engineers that designed the SLE66. It's a whole different family, probably a bunch of young guys. Their shield is worse than the 66 was. So let's get into it. So we'll talk about a couple different companies. In fact, you can pick who you want to talk about first. We could talk about Atmel, ST. Somebody said ST. Your mouse isn't working again. I don't know how it works. I'm double clicking. Okay. Yeah. Yeah, but I'm looking for something else. Okay, so the chip was basically polished. This was you guys want to hear ST. So here's what it looked like on Metal 3 after it got polished. So you can see, this had a ROM. It had a ROM right here. Where's the pointer? So you had a ROM, a read-only memory right here. You had double EEPROM right here. And you had a large SRAM down here. And, basically, this chip had a shield on it that if you break the wire on the shield, the chip would erase its double EEPROM. So all the contents of this area, which is where all the secrets are stored, are gone with one break of this wire. So the shield is missing because I don't care about the shield. I go right through with the fib. I just jump it. With one wire, you can undo the shield on this chip. It's not a big deal. But ST's been doing, I have to give credit to ST because ST's been doing shields on their devices since 1996, 1994, something like this. So they're the pioneers of the shield. They really are. And their shield today, it's okay. It's not the best. So that was Metal 3. You can see here's Metal 2. You can kind of see as we're getting lower on the chip. So again, I took, several different devices, polished them on a polisher or a lapping machine, polished them down with this silica solution. And, this is the next layer down. So this is 2 chips now that got destroyed in the process. But I went through probably more like 10 chips to get 4 perfect chips. We've got Metal 1, Metal 2, Metal 3, and Poly. Poly's the transistors, Metal 1 is the logic, and then everything here is all going to be wires routing like on a PCB. Okay, then we got another one here. Let's see. So here's Metal 1. It's looking even less and less dense now as you get lower in the chip. And now you can start to see, like, here's drivers to output the EEPROM. Here's drivers to output the ROM. Here's a math coprocessor here and here. So you can totally tell nothing you're after is going to be in this area. This is all basically static RAM almost. Here too. This has to do with their modular arithmetic processor for asymmetric crypto, symmetric crypto, stuff like that. So we don't care about anything down here at all. And honestly, again, like on every chip out there in the world, where does it boot up from? It boots up from here. So where are you going to start tracing from? You're going to follow from here and you're going to go into this core somewhere. Now, this is a fully synthesized core. In the past, they used to run microcode. So they'd have these tables of these micro ROM tables inside the chip that would be present, for example, here. And it was so easy. You just basically walked up to the edge of it and you knew the flip-flops were right there, latching the instruction into that microcode to execute. Okay, so I'm kind of jumping the gun here, but so here's like from the Photoshop where the instruction register was in the chip, and you can see like I was drawing. This is basically all the layers got turned off, and I made a JPEG out of it. But you can see like where I was drawing in Photoshop. This chip would be a waste of time for Oliver's tool. Oliver's tool is better for like the Samsung chip from yesterday. But this chip is very fun. And this chip is actually pretty complex compared to some of the other devices we'll talk about. But you can see here like boxes with a question mark. These are probably flip-flops, most likely. Okay. Here's the poly while this is opening. So you can see the poly, it gets even sketchier. Now these chips, these are just 5x images on an optical microscope. 5x is just an overview of the chip. It's literally like 2 or 3 pictures, probably 4. 1, 2, 3, and 4. Stitch them together, you're done. So this document is about 7 gigs. I believe it's either 100x optical or it could be 150, but it's probably 100. So I just have to wait for this to open. Does anybody have questions while I'm talking? Nobody? Okay. Yeah, so ST's been in this business for a long time. EM Micro, we'll talk about them a little bit too. I only have an hour, so I don't have much time. EM Micro needs to get out of the smart card business. I broke every device I've ever come across from them in minutes. And it's really sad. They don't want to work with me, and they just continue to make these devices that are just silly. Okay. So here you can see a zoomed out picture, and it looks like nothing is turned on, but I have some boxes highlighted. So we can zoom in. Now this is only the digital block. This is, you saw the overview of the chip. This is just, the ROM is coming out over here and feeding into the core, I believe, up here somewhere. And then the EEPROM is above us. The EEPROM is up here. But I don't care about that. I just want the digital area. It all depends on time, really. How much time is it going to take me? And imaging the EEPROM at this resolution would be almost insane, because every picture you take looks like the last picture. So the stitching software has trouble to stitch these types of memories together, because they unless it knows exactly, this many microns into the picture align the 2 pictures. It is very hard to stitch memories, but Keyence makes microscopes that will do this. They do it very well. You can zoom in really high res. Let me see. ST did a nice job. This is a 350 nanometer. I think I forgot to say that. This is a 350 nanometer design. This is like 2005. It's kind of old, but like I said, you have got to crawl before you walk. So here's metal 1 on the chip. And, the reason we're here in this area is because the data bus took me there from the ROM. As I said yesterday, the ROM output was to that left over here. And we came in, like I've got a number 8 here. I don't know what that's for. So you can see ST put down metal sometimes. I don't know why. Like these plates, this is nothing. This is just sputtered metal. It doesn't do anything. In fact, if anything, it helps me with my polishing. Because when I polish, when there's an open gap, if there's an open gap here, sometimes I'll get a hole. Like Chris Gerlinski talked about yesterday with wet chemicals. You'll get a hole in the oxide deeper than everywhere else. So let's turn on some layers. You can see here, there's more tracing. So what ST did was, the overall, here, you can see here, actually, I have a comment, XOR 1, XOR 2. So these are XOR gates. Again, a 1 and a 0 is a 1, a 0 and a 1 is a 1, 0, 0, 0, 1, 1 is 0, 2. So this is the classic cryptographic function of an encrypted ROM, is an XOR. Fall through an XOR and that's it. But ST did something really cool. ST decrypts with XOR 1, the fetch. So the bit that there's 8 XORs, because it's an 8-bit data bus on this particular chip. On their newer chips, they went to a 16-bit data bus. On the ST23s, which are 90 nanometers, I showed a snapshot of it yesterday. Oliver Thomas and I, with Oliver Kummerling, did some work on the ST23. When was that? Back in like 2009? No, ST23. 21 we did too. That was different though. The 23 was a 90 nanometer. 2010 maybe? Something like this. Yeah, so ST's been at 90 nanometers on some of their devices since at least 2010. So, and I don't know where they are today. I haven't followed them. So let's see. There's lots of comments here. So we can turn on layers. As you can see, this is perfectly aligned, perfectly polished. So this is the difference with, like yesterday, Chris Gerlinski was talking about hydrofluoric acid. So this chip, I probably did dip it in hydrofluoric acid, but not for very long. And then afterwards, I put it on the polisher with my finger so that the polisher disc is spinning and I just have my finger on the polisher with the chip under my finger. Excuse me. And this is literally a couple minutes to get this like this. This is not good enough for a SEM image, though. Thank you. These pictures are good optical, but for a SEM, these are not. Everything needs to be white. So the vias, you can see the vias in this picture that are going up to another layer. You can see the wires. These wires wouldn't show up. They wouldn't light up in a fib or a SEM. So you can see metal 3 turns on. Metal 3, though, metal 3 is white. So metal 3, I polished perfectly till it's white. So, and the reason was probably I was going to load this chip into the fib later and then do my what I would call my like mask set. So, you know, these guys that design it know exactly how many microns to move over to go to the instruction register, for example. But in my instance, I have to make this myself. So this chip I would load into the fib. It's white. It's perfect. It's polished till it's white. So these are bare aluminum wires now. I would move to a bond pad within kind of close to the area I'm going to go from. So, for example, the bond pad could be up over here, and I'll move, you know, over so far and down so far in microns, in micrometers, in the fib, and then drill a hole like you saw yesterday on Samsung, and then in that hole I can see deeper. If I keep milling, that gas that I run, that xenon difluoride gas, is gonna etch through the shield and leave those shield wires intact, and then it's gonna mill down to these wires here. So I move over, for example, 500 microns down 600 microns. I make a big hole, and I look through the hole, you know, with the machine at this layer with the shield still intact. Do you follow me? Kind of? Okay. I showed it to you yesterday on those pictures. So you can see, I have so many comments. So basically, tracing the ROM output brought me here. And you can see here's the instruction registers in the device. So it's game over. The one thing I have to say about ST that I like, the second XOR gate that I showed you, is for bus encryption. So, every peripheral in the chip, you know, EEPROM, ROM, it goes through a scrambler basically. So after every reset, if I'm putting a needle down on the main data bus in their chip, after every reset, it's going to be a different value because of this randomized XOR. It's a random number that they generate on power on reset. And it's very smart. ST's got a lot of good ideas. So you can see where we are. We're not really on the edge. Usually the instruction register is not going to be dead in the middle somewhere because it's got to decode everything. So it's going to be like in the corner somewhere on the edge. It's not going to be in the middle. It's, you know, then it would be like a tree, you know, branching this way and that way and this way. So it's very logical, very methodically laid out, even though this is automatically generated, with their software when they did their layout. I'm not really going to talk too much more about ST because I don't have time. But we got here from the ROM. The ROM took us to this spot right here. You know, went through 2 XORs. Second XOR was that bus encryption I spoke about. So where can I put a needle down? I can put a needle down to listen, just to listen, in between XOR 1 and XOR 2. XOR 1 decrypted the ROM fetch. XOR 2 re-scrambled every reset the data bus. So we put a needle down in between XOR 1 and XOR 2, and we can listen to what the chips are running. But we can't do anything. We could do a glitch. So we could modify some instruction to maybe it's a loop that reads EEPROM out and sends it out the ISO 7816 data port, which is a UART built into the chip. So, you know, maybe it's going to read EEPROM and send a byte out to the outside world. So I could glitch that with a needle. So there's things that you could do, but this chip runs on its own internal clock. So you'd really need a needle for the clock source, and then you'd need a needle to do the glitch. So that'd be 2 needles you'd have to put down. But that's not hard. 5 needles is usually about the max I use. And that's a worst case situation. So let's talk about somebody else. Let's talk about Atmel. Atmel's out of the business today. They sold a microchip as well. And here, well, this opens. We'll look at some other stuff. So you can see like I've got a picture called fib points. So you can see here again, it's a polished chip. I could put this in. This is another 350 nanometers chip. This chip had no shield on it. This is an old Atmel chip. But again, the Atmel's been doing pretty strong crypto compared to everybody else. Atmel's crypto, every value of the flash falls through an avalanche of this cryptographic function. And it's a bunch of nonsense. It's nothing you care about. And it's kind of funny because you just go to the input of the gate, you go to the output of the gate, and you keep going until you hit the flip-flops. On Atmel's, like I told you yesterday on Samsung, it's another RISC design. So again, cut the D15 line. You cut D15, the chip can't branch. If the chip can't branch, it powers up at 0, goes to 1, 2, 3, 4, 5, and I'm just listening with needles. It's great. I love RISC processors. This picture, I don't know how large it is. I think it's at least 10 gigabytes though. What's that? 16 gig? Okay. He's good. You saw it, Oliver? Yeah. So you can see in this picture, in this JPEG, I've highlighted all the flip-flops of the instruction register, and I've got lines drawn. And these lines are the data bus bits. Now the data bus is out of order. So again, what I talked about yesterday, I know the first instruction the chip is going to do is going to be a branch. So, and before I even cut that D15 line, I'm going to listen. So I'm going to put down needles and I'm going to just walk on the bus. Walking means I'm listening and I'm not going to change anything. I'm going to let the processor run. So it's going to give me back the answer to reset or whatever the chip did for its functionality. So you can see these are my fib edit lines, like right here. And these are the flip-flops buried. They're buried. But every line I needed to get to was on top metal. So you'll see in my picture, 0 to 15, but then I have some C code that takes my captured output and it reorders the bits. And it's trivial, but it takes about an hour, 2 hours to figure out the ordering. And then there was a couple bit errors, like, you'll have a couple bit errors and you throw it through your disassembler and you realize, okay, the running code that I just captured doesn't look right, but it's pretty close. You flip a couple, swap a couple bit positions, you're good. They're not doing any kind of inverting or anything. Everything's direct. So once you're through the crypto, you have direct values. So you can see here that this is a total of 15 of them, and there's 15 purple colored lines. And again, this is like taking candy from a baby for me. I mean, once I do my images, it's game over almost. Only the chips today that I'm working on now are hard compared to this stuff. This stuff is very old, but I like it. I like the old stuff. I miss the old days. So you can see here, the flash was right here. But I'm not going to image that flash because, like I told you, it's all looks the same under the microscope at 100x, 150x. So the only thing I cared about was the flash outputs and the logic, which was here. And there was a static RAM here, I believe, or there was a ROM, but the ROM was for cryptography, for their math processor. All of these chips we're talking about have a math coprocessor inside. So they could do asymmetric crypto algorithms as well as symmetric. They have DES, RSA, elliptic curves in some cases. So here we go again. Same thing again, optically imaged. Now, this chip came out in probably 2000, 2002 maybe. This is an old device, but Atmel's been doing fully synthesized cores back when ST, for example, and Infineon were still doing a microcode core with microcode, like I talked about earlier, where the instruction registers point into a table. And in Infineon's case, the table was like the address into the microcode to run from for a jump or for add or for subtract. So you can see here as we zoom in, the picture's pretty nice. Now, and again, this layer was polished till it was white. So this layer is good for the fib. We can turn off this. Now you can see here, this layer is not good for the fib. The only thing I'd see in the fib are the white dots. That's it. Everything else would be black. I could spray some platinum down, which you've seen on some of the pictures from Chris yesterday. That cross picture he showed you with a ROM, that was where I had sputtered platinum. So I sputtered platinum down because it was pitch black, because there was nothing to conduct. It's all oxide on the surface. Sometimes you can get an image, sometimes you can't. So you sputter some platinum down, you open the valve at a high beam current, and it deposits. But other than that, you still, this needs polished more for a fib. But you can start to see, as you turn off metal 3, you can start to see the transistors below. And you can see, like here, it looks like I don't have poly on this chip. I thought I usually do, but if I'm missing the poly layer, which is how you can tell what a gate's doing, like you can't tell what this is doing. You can see here's an output, or here's the output, here's an input. So this is some type of 2-input NAND NOR. It's something. It's not an XOR though. It's something smaller. So this is a NAND or a NOR. And given right here, I can see the P. This is VDD on this chip. I can tell by I can see the well right here in the picture. So you can see like the well goes from there to there. This is what's so nice about the old generations. You can learn a lot from them. Okay. So I've broken so many Atmels, I didn't need poly on this. You can see here's some tracing. I'm looking for the instruction register, but I haven't been in this picture for years. You can see here I was tracing through. The flash came out on top. So the flash outputs are up here. And this is maybe one of them. I don't know. But you can see here I was in here drawing. If you don't customize the logic in these off-the-shelf chips today, you're going to get hacked. It depends if your target is something of value to somebody. For example, a toner cartridge, or satellite TV. Today, every satellite TV access card used has heavy modifications to the IC. Nothing is off the shelf. DirecTV has, I believe, 4 different smart cards in the field right now at the same time. Just in case one got hacked, they switch off that card. They only have to, release 1 million of these chips, not 17 million if they got hacked totally. Dish Network, same thing. Dish Network's using an SLE 88, but it's not off the shelf. It has changes to it, to the silicon. You can see here's more drawing and stuff. So this was a 3232C, if anybody knows this chip. So this is an old chip. Andrew, how much time do I have? How much? 20? Okay. Atmel came out with some newer stuff. Here's a newer AVR. So these are all Atmel AVRs. Here they've got a little bit of EEPROM here, some static RAM, more static RAM, and a ROM. The ROM was a mask ROM, so Chris Gerlinski could have thrown it into his program and tried to get an output from it. But it's heavily encrypted. And the first thing it does when it comes out into the logic is it goes into a flip-flop. So why did Atmel output their ROM or their flash, or their ROM actually, sorry. Why did the ROM come straight into a flip-flop first? Because I told you yesterday, you hit a flip-flop, you're usually at the instruction register. But that's not the case with Atmel. Atmel wanted to hold they wanted to prevent me from freezing the flip-flop, because if I freeze the flip-flop, I'm freezing the encrypted ROM contents, not the decrypted ROM contents. Do you follow? So Atmel thought, I'm going to put a flip-flop first, latch that output, and then trickle through my avalanche of crypto, and then it just appears into the logic area to execute the instruction. However, again, you cut the D15 line, and the chip can't branch because it's a risk. It's same thing on these car chips, automotive chips, these risks. On this one NXP chip, I had to cut 13 and 15. We were talking about it yesterday, Oliver and I, at lunch. And I don't remember why I cut 15 or 13, but I had to cut 13 for some reason. 13 and 15 to make it not branch. And then I just listen with my needles on the opposite side of the cut, and I suck out all the ROM contents or the flash. It just depends what I'm up to. So this is, you can see here again, the flash is missing, the ROM is missing. All I'm after is the busing, routing, the wires, and the core. And this is, I believe, 150 power, magnification. So I'll just real quick zoom in here. You can see this is a 5 metal layer chip. So this is a 250 nanometer, like 250. Give me a second here. This is like a 250 nanometer 5 metal. So you can see metal 5. Boom, there's metal 5. There's not much to see. Metal 5 is basically just hiding below, the routing below. There's a little bit of routing on the surface, but all of this metal you see here is what I call CMP fill. So it's just fill, and it actually helps me when I polish. It keeps it more planar. So if we turn off, let's see here. Trying to turn off these layers. You can see as we go deeper, we need to zoom in more. So we're hitting the spectrum Chris talked about yesterday, where it's almost time to go to a fib or a SEM to image this. Because even though I can trace on this, it's not really, it's at the limits of the microscope. This is 150x zoomed in on a 250 nanometer process. Today, Intel's at like 10 nanometers. Now, none of these security ICs are going to be anywhere close to 10 nanometers for years. It's too expensive. They don't make enough money on these lines to do it. So the average chip I see today is a 140, 180 nanometer process. Usually, some stuff is 90 that I'm seeing. The smallest I've seen is 65. But you can see, so the layers these are all aligned, optically imaged. Now, I don't have poly on this, and I would need it. This was pleasure. This wasn't a job. This was just me messing around one weekend or something. So I did this. But you can spot, this looks like a flip-flop right here. You can spot stuff. You can spot some things pretty quick. But this is their metal 1 layer. I don't have the poly. The poly wouldn't have looked good though. The poly would have looked like crap because this is such a small process. People think, 250. I want to see you put needles down on a 250 nanometer chip, or I want to see you put needles down on a 180 or a 140. It's pretty small. It's, people take it for granted because AMD and Infineon is making all these small processors today. Okay, let's talk about EM Micro. So EM Micro, Chris Gerlinski helped me with this actually. So this was their boot ROM. So this was polished. This is called an EMTG-I2C, something like that. It has an I2C bus, and it got used on PS4 for the PlayStation aftermarket controllers in China. So Chris and I imaged this in the fib. This is the picture said it was 20,000 times zoomed in. So this is 140 nanometer shrink. And it's zoomed in 20,000 times in the machine. So we can read this. Chris read this no problem. And I think he had a little bit of some swapping to do or something with bits. I don't think he's here. I don't know if he's here or not to ask him. Oh, he's here. Yeah, do you remember what you did on this?
Yeah, there was pretty straightforward bit swapping.
Was it? Yeah. So he gave me the ROM dump in minutes, where if it hadn't been for Chris, I would have had to basically cut the output of this ROM. So on an 8051 and on ST, sorry guys, if I cut the data bus lines, all of them, the bus floats to FF. And FF walks. FF doesn't do anything. FF is like store X on a ST chip. It's going to be on a 6805. It's going to be like store into X, some value like, or something. And on an 8051, it's like a move or something into R7, something like that. So FF works great. So if it wasn't for Chris, I would have cut the eight output lines of the data bus and then listened opposite of the cut. So the CPU thinks it's getting FF, but on the other side of these cuts, I'm really listening to the data coming out of the ROM as it goes to address 1, 2, 3, 4. So the EM Micro chips aren't secure, but they're more trivial to break than anybody else because they take steps. So once we got the boot ROM out, we had to get the flash contents out. Now, the chip that I modified, if I cut the boot ROM's data bus outputs, that chip's garbage when I'm done. That chip's just to read the boot ROM, and that's it. So I'm going to throw the chip away or throw it into my jar, and it's for later. this is what the chip looked like. This is polished. So this is ready to go into a Fibber SM again. So you can see it's white. It's beautiful. This is a beautiful picture. You can see here's their flash. Here's their static RAM. And here's the boot ROM right here. So you had 4 bits on this side and 4 bits on this side coming out into the core. Now this chip, we dumped it and we got weird values back from it. Like it wasn't, we both knew, Chris and I are talking about this and we're like, we know it's walking. We know the chip's going from address in the flash from address 1 to 2 to 3 to 4, but the code doesn't make any sense. And it's not Hemingway. Something was up. So then, I get some samples of the IC from AMD Micro and the samples, I pulled my own code that I load in. I load in into the flash 1, 2, 3, 4, 5. And then I pull it with needles and it's legit. I see my code. So Chris and I are scratching our heads what the heck's going on here? So it turns out, depending on their OTP, if a one-time programmable area of their flash, all of these smart cards have what they call OTP inside. So they have a serial number, the wafer position, the X and Y coordinates of the wafer, and they use this as a generic serial number, a unique serial number per chip. And this area is not supposed to be temperable. You're not supposed to be able to overwrite it. It's supposed to be OTP, one-time programmable. So it's set at the factory and that's it. However, on AMD Micro, you can overwrite it. So Chris and I just overwrote the OTP values with the dump from the crypted chip and then basically read the chip back out and it was in the clear. So we used their own crypto against them. You follow me? No? Kind of? Okay. So to get the code out of this chip, you have to first understand the boot ROM. Then you have to study the boot ROM and you have to look at it. You have to look for an address to strap to jump into flash because you don't want the boot ROM to power up. If the boot ROM runs, as Chris said yesterday, all of these chips are doing self checks on power up. They're setting trimming values for, VPP, the programming voltage for the EEPROM, for the flash, stuff like this. They're setting up their PLL, to run. This chip runs on its own internal frequency. All of these chips, except that Atmel, the first Atmel I showed you, run on the internal clock. So you've got I think we strapped it we found some instruction that jumped into flash and the addressing on this was out of order too. But here's the easy way to figure out the addressing scheme. As soon as I cut the data bus, the 8 data bus bits, the chip, as it wants to boot up from its ROM, it starts to boot up. And instead of booting up, it goes, 1, 2, 3, 4, 5. So now I know the address is going 1, 2, 3, 4, 5 as, that's what it's doing. So then I put a needle down on each one with an oscilloscope and I just measured the waveform, because it's incrementing sequential. It's linear code extraction at this point for this area only for this boot ROM. So that gave me the address ordering of the address bits because they were totally scrambled. They were, address bit 4 wasn't in position 4. It was in position 7 because how can I strap? I went into the fib and I strapped an address. So I changed, instead of letting the address increment linearly, or whatever it does in its runtime when the chip runs like normal, I strapped the address to 100. So instead of powering up at 0, it went to 100. And then it went to 101, not 1. Then it went to 102 instead of 2 because I physically modified the address bus on the inputs of this memory. So basically what I did was I made the ROM skip all of its self checks because if the ROM knew that what I was going to do to this flash, the ROM would erase it and put me back into the bootloader mode because these chips have a bootloader where you can download into this flash. So the flash drivers were here. And the game's not even over. Once you do all this work in that boot ROM that I talked about, and this had a shield, by the way. This did have a shield, and the shield went diagonally across the chip. And again, another case in point, the shield didn't work. So, I just made holes to the shield. No big deal. But then I saw the same thing again. I saw randomness where it would just stop talking to me. And when you're in a 5-hour fib edit or a 4-hour fib edit, if you rent the machine, it's $350 an hour. So, you have to own the machine, honestly, to handle these jobs. I'm constantly powering up the chip while it's in the fib. I have a DB25 electric pass-through connector, so I can run the device inside the chamber while I'm working on it, because I want to make sure it's still alive. Because the types of edits I'm going through, to get to here, I have to go through that shield, that diagonal, the zigzag lines. So once you strap that boot ROM to basically just power up and jump into flash, you have to cut the flash outputs. So you have to understand, where's this flash even outputting? You can see what it looks like. Is it outputting here? Is it outputting here? Well, it's outputting here, just to save you guys. But so this is there are 8 output bits. Why they did it like this, I don't know. But this was a fun chip to work on. This is, I think, only a 10x picture. This is a 140 nanometer shrink. It's 5 metals, 5 or 6 metal layers. But when you see what I did, this is all I did to crack the chip. I didn't even do full images of the logic or anything. Like, this is a fib picture from the Fibber SM. And you can see here, I'm measuring. So from the edge here to there is 2.6 microns. From here to here, 5.8 microns. And the reason for these measures, this is the flash bus. So this is the output of the flash. So I've already strapped I've strapped the boot ROM. So the boot ROM's basically not doing any of its self-checks anymore. Now, and then I've cut the flash. So I've cut the flash over here somewhere. So I literally just severed the lines. So the wires are cut. So now the bus is floating. So the bus is seeing FF from the flash. And meanwhile, here on the left side, I'm seeing the data. You follow? Okay. Yeah, here, now that looks, can you guys see this? It's real dark. Can people see it? Or it's real dark, but this is basically a resistor on the surface. I have no clue what they're up to. I don't know why it's there. I don't really care. I would mill a hole right through it. I'd move over so many microns on X and Y, like I keep talking about, from a bond pad. And then each measurement, you can see here, I have them all measured. And here's a clock. I need a clock. I gotta get a clock, because even if I cut the flash outputs, this chip runs at like 25 megahertz or something internally. So I've gotta listen I need a clock signal from inside. And because it's running in what I call linear code extraction, I should say, Oliver calls it too, where it's sequentially walking through time, we almost any line will work. Even an address like A0 line would work, because A0 is going 1, 2, 1, or 1, 0, 1, 0, 1, 0, 1, 0. That's a clock. That's perfect. So with 2 needles, I can read this chip out once I do my fib edits. So these are the guys that I said they need to get out of the smart card business. They make these I'm going to say half-ass, but I shouldn't talk like that. But they don't make good products. So you can see here, I've got comments in this picture, but this is all I generated to hack this chip. I didn't do the images like you saw. There's little notes here, 79 microns by 46 microns over from the left corner. And looking back on this is a bad note. I have no clue what I'm talking about. I don't, and then you can see here, I'm like, test pad is 77 microns over, blah, 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 with an arrow. And the bond pad was probably right here, right in this area. That's what it looks like. I'm out of time? Okay. Yeah, so you can see this was the flash outputs. It was pretty easy to see, and it gets even better. This picture gets funnier. This is how easy these guys are. They're trivial. I would say they're trivial at most. So I don't know if everybody can see, but this is another layer imaged in the fib. Wasn't polished. They're really good. When you get down to 140 nanometer, you're going to have problems polishing with wet chemicals. You're going to have to use Rye-etch and a combination of Rye-etch and mechanical polishing. So this wasn't really, this is crap, for images. This is not good. And then you can see, let's see. Here we go. So there's the driver output. That's what one driver output looks like. in the device. And it's so easy to spot. This is just a couple inverters in series. Invert, in gone, or double inverters in parallel. Sometimes you'll see, two inverters together, double the power. Same thing with an IC. If you're messing with like a 7404 or something, you can use two of the drivers instead of one to get more power from it. So this is this IC, you can see here, you can see that that's where it lived. It lived right here. And there were 8 of them. And so then they had these little wishbones, what I call wishbones. You can see one right here. So here's one right here. Here's a wishbone. Can everybody see this picture? It's kind of dark. So these wishbones are going over a power rail. I don't know if it's ground or VDD. It doesn't matter to me. They're going over a power rail. And you can see here's another one. And there's my measurement, 2.6 microns away. So this was 2.6 microns away. It's basically, go to this, there was a piece of metal here that you can't see in the picture very well. And move over to the left 2.6 microns and dig a hole. Dig a hole to China, basically. Because this is down on like metal 2. And I'm on the surface. So I'm going through the shield. I made a big hole in the shield because the shield doesn't matter. And then in that hole, I put my circles down. I don't have a picture of the final chip, but it was beautiful. This was a real beautiful fib edit when I was done. Move over 2.6 microns, drill a hole to China, and boom, you hit the wire. All of a sudden it just lights up white in about 45 seconds, maybe a minute. Depends on your beam current, how strong you are. And so as I said again, so the flash bus got cut over here somewhere. I don't remember if it's this or this, but one of these was the 8-bit output of the flash. So you strap the boot ROM, you cut the flash, and it's game over on every EM Micro chip they've ever made. Let's see if I have anything else. I think I'm out of time though. Yeah, here's what the EM microchip looked like with the shield. So I keep talking about these shields, and you guys are probably like, what's he mean? You probably have some type of an idea. And this is what it looks like. It looks like a mirror on some chips. Oh, I didn't talk about Infineon yet. So here's some type of test pad. Here, I don't know what these pads did, but this was the I2C clock, I2C data, ground, ISO 7816 IO line, VDD, reset, and clock. Even though it has a clock line, you don't need the clock line because the chip runs on its own internal clock. This clock is only for the UART, for the ISO 7816 UART. I2C doesn't obviously need an external clock, So basically, the flash was like right here in the chip. The boot ROM was over here, but it's buried underneath this. So you've got to get through this first. And this is just a diagonal line, so it's going diagonally across the chip. So it's cute. I mean, this doesn't do anything, guys. This is like a 10-minute detour, and when you're on the fib, it's honestly, the shield technology you can bypass every shield I've ever seen with one fib edit if you do your logic. Oliver and I were just talking about it yesterday because at the end of the day, just like those alarms in the Samsung chip, at the end of the day, it's one wire that turns on a 1 or a 0 that says, hey, there's an alarm going on in the chip. It's not, 32 wires like you see on the Surface, for example. So Infineon, I've talked about this, I beat them to death, but somebody wanted to hear about Infineon. So real quick, we'll go over some Infineon stuff. This is what a 66PE looks like. This is an old chip today. This is a 180 nanometer process. I believe it was 4 metal layers, I believe, with the shield. Now, Infineon did something really neat. I've never seen this before. They put their bond pads in the middle. And I heard from a guy that works at Infineon, he told me that the reason for the bond pad layout like this in the middle of the chip, because there's a shield all over here. This is all shielding. And if you mess the shield up, the chip's dead. But he told me it was for what's that called? Bump process or something? Where there's balls, where the balls are flipped upside down on the package. It's for packaging, bump, something like that. Anyway, so this made it challenging because usually what happens is the bond pads are on the edge. They're over here, and there's no shield around the bond pads. So you'll have empty space, because once I throw it into acid, like Chris showed you yesterday, there's going to be wires still attached right here, on these 5 connections. So I'm going to pluck them off with tweezers. When I pluck them off with tweezers, you end up with this. You end up with 5 balls. These are gold balls. So I could dip this in mercury. I could soak this chip in mercury for hours, and the mercury would eat the gold away. But it takes hours. I don't have hours. So you glue the chip down into a ceramic dip, like I showed you yesterday with the Samsung, and you wire bond these 5 wires. But as soon as I put a wire down on any one of these, it's going to smash the original ball. The original ball is going to get smashed and crushed as the new wire gets placed down. You follow me? So which could have damaged the shield. If I damage the shield, the chip's garbage. Throw it away. Get another one. So Infineon's not as new as ST. ST's been doing shields. They're the pioneers, like I said. But Infineon's got a pretty good shield going. You can see here, but Infineon's problem on the 66, this is not the same with the 78. The 76, 77, 78 are fully synthesized cores. So there's no microcode. But you can see here, I only imaged, this is 150, no, this is 100x, it says. So this is 100 times zoomed in. You can see in the red, I've highlighted the data bus. So Infineon will brag about their crypto and stuff, but in the heart of the CPU, here's their data bus. But this is a CISC processor. This is an 8051. I could cut the bus, but Infineon is doing memory mapping. So they're doing a lot with paging memory. So you have to let the processor run a bunch of instructions to get the memory maps mapped in, or else you'll get the basic 0 to 32K memory block. That is maybe interesting, but it's not the entire contents. So to get the entire contents out, you have to let their memory encryption decryption block get set up by the code, by the ROM code. So you can't just cut the bus on this. Cutting the bus wouldn't help you really. But what you can do is you can put a needle down on the instruction register, which is right here. I just don't have it highlighted. But there's a wire in here. I'm not going to show you which one, but there's a wire in this area that if I put one needle on it, it freezes the last instruction executed. So the flip-flops are frozen in time. So the flip-flops, instead of toggling for every instruction, they think it's still add or do this. But on this particular Infineon, rather than abuse the instruction latch, the instruction register the clock line to it, I glitched on the data bus. So I actually glitched, and the data bus, Infineon is really bizarre. The data bus was 0 to 7. So this is 0 and that's 7. And once you do 166p PE, whatever generation of the 66, you've done them all. It's just a matter of where did this core move to in the layout. So layout to layout, it will change. But here's the reset line, the internal reset line. Once you understand the core of the 66, it's game over for every 66 out there if it's your intent to get the code out. But they can be a pain in the butt, as I said, because of the memory paging. STs, you guys are doing memory paging too on the ST19 stuff. So you can see here, this is one table of the microcode. So basically the instruction register was here, and it points into this table, and it gives an address to another microcode table of where to begin running from. Go to address, an add is at microcode line 10. A subtract is microcode line 20. Stuff like this. The 66 I think it's dead today. Here's another one. Here's the 66 with the shield removed. So this is not the same chip I showed you with the shield, but you can see it's the same thing almost. You got the bond pads in the middle. Here's some EEPROM. Here's some RAM. Here's a ROM. Big ROM, pretty big ROM. And then here's the core. Now, one thing I don't think I talked about this too much in the past. The core has light sensors, optical light sensors. So they're looking to see if someone's using a microscope with light and their shield's been tampered with. But the light sensors won't work with the fib, because when I'm done with the edit took about 6 hours. When I'm done with the edit, it looks like this. So you can see here's literally in order. It's going to be 0, 1, 2, 3, 4, 5, 6, 7. And then this one here should be that instruction register clock line. that I'm talking about, that I can freeze it. If I freeze it, it makes the processor walk. Because I can glitch on here, or I could glitch a bit of the data bus. I can change an add to be something else. If it's 21, I can make it 20. If it's 20, I can make it 21. Or I can make it, I could put a needle on bit 7 and I could OR an 80 into the opcode. So instead of seeing a 20 opcode, it's going to see 20 plus 80. It's what, an A0 opcode? I don't know what it does, but I'm just making this up hypothetically. So you can see this, you can see in this picture, you can't see it. I can see it. I can see it on the Mac. If I zoom in, there's wires. There's wires here. So on the Infineon Shield, I had to make these holes. These holes there's 3 wires cut, 3 shield lines, 1, 2, and 3. And then there's a plate of metal underneath. So Infineon put up the shield, a plate of metal, and then the CPU core. So this is actually, 3 shield lines got cut. This hole is like 5 microns long, if anybody knows microns. So the hole is usually I probe like a 5 micron window, 3 microns, it depends. The bigger the hole, the longer it takes. So then I removed the shield lines, each one. Then I had a perfect plate of metal here. It lit up white. It was perfectly white. And then I used a high beam current and I removed the metal everywhere. And then now it got black again because the metal's gone. So, metal will light up. Black is absorbing the beam current. So black is charging when you're in the machine. So then in the middle of the box, I knew the wire was right there. And I knew the wire was right there because if you look, here's my alignment right here. So in between 2 shield lines, I dug a hole deep. I dug through that metal that's blocking that metal plate. I dug through the metal plate, and then I got to the wires. And then here's all my wires I'm after. So, I'll move on the fib. I'll move over to here, and then I'll move so many microns here, make my hole. Move, go to that wire, move over here to make that hole. So this takes, like I said, about 6 hours. It's a long process. So if you were renting time on a machine, I don't think you'd be successful. This is a very difficult edit because of the plate of metal, the shield removal and stuff. But if the chip even knows we broke the shield like I did, it's going to lock up. So on every 66, the core moves around. It's not in the same spot ever. It's moving around unless it's the same chip, of course. And then I go to the top of the chip. And I go to the bottom of the chip and I open the shield like you can see here. Now you can't see in this picture very well, but there's connections underneath. So this wire connects to this wire and this wire connected to that wire. So it was 4 circuits. The shield was consisting of 4 different wires running across the entire chip. So what I would do is I'd go from here to here. And that's enough room for me to open those 8 holes, 7, 8 holes. So I go from here to here and I jump it. So I'd say, okay, I know based on where I am in the chip that shield wire 56 connects up over here to number 20. So I just make a bridge across, I drop platinum or tungsten across this entire distance away from my fib edit area, somewhere in the chip, just away from where I'm going to do my actual edits. And once I do these 4 bridges, I can open a hole anywhere in this area I want to. And the chip has no clue. So Infineon's they've made leaps and bounds. I'm not a big fan of their 76, 77, 78 series. I'd prefer ST over Infineon for their architecture. But Infineon's 78, I wouldn't trust it. They're bragging about how the core is split into 2 halves. And it's a bunch of bullshit. At some point in the CPU core, it knows how to add 10. Or it knows how to subtract 20. And Infineon runs around touting never at any point in the CPU core is the opcode in the clear. And that's bull. It has to execute something, it has to run code. So that's all I got.
Questions? Do we have questions?
Hi. First of all, impressive work. Congratulations and thank you very much for taking your time to sharing with us. My question is going to be about mobile phones. mobile phones, like smartphones. Nowadays, most secure phones rely on boot of trust by relying on eFuses. So, did you have any time to take a look at eFuses such like Knox on the Samsung? And did you have any chance to tamper with them?
I haven't. It hasn't been an interest to me. I have never seen them. I mean, if you can spot single cells of non-volatile memory, you can spot them very fast. They're very large. To do a single cell of double EEPROM for like a fuse bit in a chip, it's a large block of logic just to get that done. So you can spot single cells of double EEPROM, for example, in the ST processes. They have their main, the EEPROM, double EEPROM, and then they had, some type of very small, non-volatile memories. I don't know what they were for though. They could have been for trimming values. I don't know. But so to answer your question, I could find fuses like this, no problem, but I haven't actually looked into it, no.
Any other questions? Okay.
What kind of fib were you using?
I have a FEI DB235. So it's like a 2002 machine. You can buy these machines for about 300,000 used, 250, depends. Oliver just bought one. Would you say 250? Yeah, something like that. So you can get one, they're expensive. Yeah.
Have you seen any interesting countermeasures in some of the recent chips?
Samsung. The Samsung chip with the double flip-flops with the XOR traps. That was interesting. That was actually, when I saw that, it really it got me excited. My wife is like, oh, whatever, she doesn't care. I get all excited about this stuff. But yeah, the double flip-flops, I caught that. At first, I didn't know what flip-flop 2 was for, and I'm like, all right, I see the data bus though going into logic. This looks like it's the instruction register, but what's the second flip-flop for? And then one day I'm just like, well, let me follow it. Let me see where does one of these bits outputs go? And then I realized it goes into an XOR, and I noticed flip-flop 1 merged with that same XOR as it continued onward, and that triggered that. And then I realized it went to this NAND, and then I saw then the NAND goes to a NOR, because there were several NANDs. I think I showed you NAND 4 yesterday. So that was like the fourth 4-input NAND gate that I had come across only for this area. So these alarms in that Samsung chip are everywhere. Did I answer your question? Okay.
So you had mentioned that the AMD Micro, like they're really easy to hack for you, and you broke all of them. Yeah. But it seems like
not all of them, every one that I've come across.
Right. But it seems like the primary thing you're doing is that you were able to easily get the ROM and flash contents out, right? But it seems like why were they worse? Because it seems like based on your description, you were able to do that to basically every other chip of every other brand.
But they're just worse. Why are they worse? I don't know. That's a good question. Well, I gotta admit, like that I2C chip I showed you guys from AMD Micro they had encryption on their flash content. And I think it was some silly encryption when we looked at like the way it wrote into the addressing or something in the flash. Do you remember that we loaded like values in and read them back out? So, no? Okay. Anyway, the AMD Micro, like, it's just a joke because, you just have to strap the boot ROM and cut the flash lines and you're done. That's it on every one. So it's, extract the boot ROM first, understand what they're doing, skip all, make it just branch and jump right into flash. That's what you do. The flash is on. The flash just the chip needs to see I'm branching into flash from the boot ROM to throw a multiplexer switch, to throw the mux, to switch from the bus going into the core being flash instead of boot ROM. So you strap that up, you strap the address to make it just power up and jump right into flash. And then you cut those flash lines and you listen on the left. So you cut them to the right and you listen to the left. The left side is the data. Right. The right side is seeing FFs. Yeah.
So you mentioned, I'm not very good at these things. You mentioned 160 nanometer. What's the smallest nanometer footprint right now that you've seen and played with?
65.
65. You haven't looked at 10 nanometer or 7 nanometer?
No, because that's going to be a processor. That's going to be like an Intel processor or an AMD processor or a video card, NVIDIA. Those guys are the only guys doing that stuff. Everything that I'm seeing in my world is usually about 140 minimum 140, which is pretty large, but I want to see you put needles down on 140 nanometers. It's pretty small. You know, like that I2C chip that I showed you guys was literally like a 0.5 millimeter by 0.5 millimeter. It's very small.
Thanks.
You're welcome.
Have you ever attempted to do the reverse engineering on FPGAs? And if yes, how did you do signal routing?
No, not really. I've looked at some of the Xilinxes, the older Xilinx stuff. What did I look at? I'm trying to remember which one. I think it was a Spartan years ago, though. I use FPGAs every day. That's how I stimulate I stimulate these chips that I work on with a custom FPGA board that I designed with my dad. And, it generates a clock to the chip, and it has I2C, and it has SPI bus, and it has ISO 7816 UART. It's got everything. So I just, I use this FPGA board to talk to the chip as well as to capture my data. It has 2 large static RAMs. And so I capture each bit, because whenever I'm capturing the data on these chips, it's with one needle. If I'm using 5 needles, it'd be like on an old ST chip, and it'd be like on, like an ST16 back before I had the Fib. So it'd be like one needle on the shield to fix the shield, because the shield was just VDD back then. It was just a VDD line going across the entire chip. And then it'd be like one needle for the clock and one needle for the data bus bit. And I don't even know why I'd need 2 more. But, and then, that's it. Oh, maybe one to glitch it or something. Yes.
What message would you give to all these 4-chip manufacturers that you exposed today?
Don't use these chips off the shelf. You've got to customize them. I mean, unless you're some startup company with no money, there's no reason why Infineon or ST won't help you customize the logic. ST was bragging a few years ago in their preliminary documentation. They were saying, custom logic block or something in their ST19s. So they were hinting, basically, hey, we'll help you to change, to add like your own little ASIC into the chip. Because that would make somebody like me go to Oliver for his tool, for his automated reverse engineering tools. Because, I didn't show you yesterday. Let me see, I can find them. On that Samsung chip, I started to make schematics of the crypto block. XOR decode. So this is real world. This is not Oliver's world. Oliver's tool would have done this in seconds. But you can see here, I'm starting to like put their cryptographic block back into schematics. So I mean, everybody here can read that clearly. And that was, so here you can see the D1 XOR, D0 XOR, how they interacted, D2 XOR, and then I started labeling I6, I9. And, it can be a lot of work at some point. So if you did some type of customization, to your device, you'd give me a hard time. But sometimes, like in Chris Gerlinski's instance of the DC2 hack, he was able to figure out the customized DES unit, the hardware DES that the chip had. It was customized, and Chris figured it out by loading it with like known values and stuff. So you can, if it's not trivial, you can still get hacked. You never know. And again, it depends what your product is.
All right, so I think we are time. And Chris, you got 1 hour today. Thank you.